Hey everyone, today we'll talk about special limits that we solve using the squeeze theorem. Let's get right into it. So here I have a sector of a unit circle with some line segments drawn, and I kind of want to take a moment to think about these line segments and their lengths. So starting with x over here, well, we can see that if we use the angle k theta, we can actually relate this x and this 1 using sine of k theta. So since sine is opposite over hypotenuse, well, we know that sine of k theta will just be x over 1, and ultimately that just becomes x is equal to sine of k theta. And so now we can do the same thing over here for y, except we're going to use tangent. So tangent is opposite over adjacent, so that means that tangent of k theta will just be y over 1, so that just tells us that y is equal to tangent of k theta. So from all the line segments from before, we can actually draw this triangle right here. And if we want to find its area, well, remember that the area of a triangle is 1/2 base times height. So the base of this triangle is 1, and the height of it is sine of k theta. So that means that this will just be 1/2 times 1 times sine of k theta. And ultimately that just tells us that the area is 1/2 sine of k times theta. We can also find the area of this sector, which clearly has more area than the triangle from before. So if you remember, the area of a sector is 1/2 times the angle that you create the sector with times the radius of the circle squared. So pretty simply, in this case, we have 1/2 times k theta for our angle, and our radius is just going to be 1 squared. So ultimately that just simplifies to 1/2 k theta. So finally, we have this triangle here, which clearly has more area than both of the previous shapes. So to find its area, we see that it's a triangle, so we have that area is equal to 1/2 base times height. The base will just be 1, the height will just be tangent of k theta, so plugging that in, we have 1/2 1 times tangent of k theta, and ultimately that just simplifies to 1/2 tangent of k theta. So from the previous areas, we have this inequality, and I wrote tangent of k theta as sine of k theta divided by cosine of k theta. You can even rewind the video if you want to see that this inequality is true. So anyway, I'm going to cancel all these 1/2s. I'm going to take the reciprocal of everything. So that will leave me with 1 over sine of k theta, and of course the inequality sign is going to flip since I took the reciprocal. So then I'm left with 1 over k theta here in the middle, and then it's greater than or equal to cosine of k theta in parentheses divided by sine of k theta. Okay, so now I'm going to multiply by k and by sine of k theta. So that will leave me with a k is greater than or equal to sine of k theta divided by theta, which is greater than or equal to k times cosine of k theta. Now all I did was take the limit as theta approaches 0 on all three expressions. So let's evaluate some of these. So here on the left, k is completely independent of theta. So that means that this limit will just go off to k. And so that will still be greater than or equal to the limit as theta approaches 0 of sine of k theta divided by theta. And that will be greater than or equal to. So over here, if we plug in 0 into theta, we get k times cosine of 0, so that ultimately just becomes k. So now, by the squeeze theorem that we learned about last time, well, this limit, since it's bounded by k both on the lower bound and on the upper bound, the limit itself will be equal to k. So that means that we have the limit as theta approaches 0 of sine of k theta divided by theta is equal to k. And actually, this is a very important limit that we have to learn. Kind of a more general case would be the limit as theta approaches 0 of sine of k theta divided by a theta, where a is just any real number that we divide by. And that'll be equal to k over a. This formula is also really useful to know. And if we let k and a both be 1, then we end up with this very iconic limit of the limit as theta approaches 0 of sine of theta divided by theta is equal to 1. So here we have the limit as x approaches 0 of sine squared of 3x divided by 2x. So like with any other limit, let's just plug in the x value. So here we'll have sine squared of 3 times 0 divided by 2 times 0, and ultimately that will become a 0 divided by 0 situation. So we've got to manipulate something to figure this out. So we can actually take advantage of the properties of limits to break this up into a product. So we can actually write it as the limit as x approaches 0 of sine of 3x times the limit as x approaches 0 of sine of 3x divided by 2x. So based off of the formula that we just learned, this right limit right here just goes to 3 over 2 because that's our coefficient here and that's our coefficient here. And then this limit right here, well, we just plug in the 0 into sine of 3x. Sine of 3 times 0 is sine of 0, and that's just 0. So we have a 0 times 3 over 2, which is just equal to 0, and therefore our original limit is just equal to 0. Now we have the limit as x approaches 0 of tangent of 5x divided by 3x. So once again, let's plug things in. So we have tangent of 5 times 0 divided by 3 times 0, and that will also be a 0 divided by 0 situation. So let's manipulate some things. I'm thinking that we should write tangent of 5x by its trig definition. So we'll have the limit as x approaches 0 of sine of 5x, and then that'll be divided by 3x times cosine of 5x. So once again, we can break this up into separate limits. So we'll have the limit as x approaches 0 of 1 over cosine of 5x times the limit as x approaches 0 of sine of 5x divided by 3x. So now we can use our formula that we just learned. This becomes a 5 divided by 3 because of our coefficients right there and right there. And then plugging in 0 into this limit, we get 1 over cosine of 0, which is just 1. So 1 times 5 over 3 is just going to be a 5 over 3, and therefore our original limit is also equal to 5 over 3. So here we have the limit as x approaches 0 of 1 minus cosine of x divided by x. So plugging in that 0, we have 1 minus cosine of 0 divided by 0, and that is once again a 0 divided by 0 situation. So the trick for this limit is actually multiplying it by the conjugate of the numerator. So we have the limit as x approaches 0 of 1 minus cosine of x, and that will be multiplied by 1 plus cosine of x. And of course we can't change the value of the fraction, so we have to multiply by the same thing on the bottom. So now here this just becomes the limit as x approaches 0 of 1 minus cosine squared of x divided by x times 1 plus cosine of x. So now we can use our Pythagorean identity for the numerator and see that that is just sine squared of x. So that becomes the limit as x approaches 0 of sine squared of x divided by x times 1 plus cosine of x. So now we can actually separate this as a product of 3 separate limits. So we can have the limit as x approaches 0 of sine of x times the limit as x approaches 0 of sine of x divided by x times the limit as x approaches 0 of 1 over 1 plus cosine of x. So now let's evaluate each of these limits. So this limit right here is going to go to 0 because sine of 0 is 0. We'll have it multiplied by this limit we saw was just 1 from our formulas before. And then we'll multiply that by this. Well, if we plug in 0 into x here, we get 1 plus cosine of 0, so that's 1 plus 1 in the denominator, so that is an ultimate 1/2. So the final answer here, since we're multiplying by 0, is 0, and that tells us that our limit ultimately is just equal to 0. And this actually ends up being one of those limits that are really important for you to remember. That just about wraps everything up. Thank you for watching, and have an amazing day.